In this lesson, we'll take a look at the basic coding for generating classification trees with R. We'll not be looking at some advanced features like generating ROC charts or using ROC charts to find the cutoff probability and so on. We'll not look at any of those things, or pruning or cross validation. Those are things that we'll add on in subsequent lessons. In this lesson, we're just looking at the bare bones coding for classification trees. We'll look at how to generate, print, and evaluate classification trees. So we already know that we use the function, the library caret, the package caret for generating partitions. So we load the library first, the package first. And of course, later on, we are going to require the rpart package in order to use the rpart function to generate classification trees. And we also would like to print out our classification trees to look nice. And therefore, we are going to use this package called rpart.plot, which provides a lot of advanced printing capabilities. Now, incidentally, there is a way to print classification trees directly just by using the print function, but the trees that come out don't look good at all. Whereas when we use rpart.plot, we can customize the printout quite significantly and make the plots and trees look pretty good. Okay, so we read the file, Boston Housing Classification, and here I'm just showing you something to set the factor levels explicitly. This will play a role not in this lesson, but in a later lesson. Okay, so for now we can just skip this step. We'll come back to this later on. Okay, now as usual, if you want repeatability of the results when any random selections are involved, then it's good to set the random seed to a particular number so that everybody who sets the seed to the same number will get the same random numbers, and therefore despite using random numbers, we'll still be able to replicate the results. Okay, so now we do the usual creation of partitions. So create data partition, and we already know that in order to create data partition using this particular function, we need to supply the target attribute and of course what proportion we want to pick. And we say list equals false because we want the result to come out not in the form of a list, but in the form of a vector or a matrix. Okay, so once we have that, SAM is just the row numbers of the selected rows, and we can therefore say train is BH of SAM, comma, so only the rows in SAM but all columns, and all the rest going to test. So BH of minus SAM, meaning anything other than SAM, other than what is contained in the vector SAM, will all go into test. So now we start actually the process of building the tree. We use the rpart function, which is in the rpart package. The package and the function happen to have the same name, that's okay. And here all we are saying is medv underscore cat, which is one column in the data frame, BH. That is our target attribute, and it has the values of low and high for the property values. Okay, so when we write an expression like this, medv underscore cat tilde dot, right? So what we are saying is, I want to build a model to predict the value of medv underscore cat using all other attributes. So dot means all the remaining attributes other than medv cat. Okay, quite often we'll have a data frame in which we've got the target attribute and we want to use everything else as a predictor. Then this is a short form for just indicating that. Now, if you want to indicate specific attributes, there's a way to do that, and later in the course we'll encounter that as well. Okay, of course, when we are talking about attribute names like medv cat, we have to tell the system, well, in which data frame is it contained. So I'm saying data equals train because we are building the model on the training data. And we just want to use some control over the size of the tree. Okay, so we say min bucket equals 10. That means we don't want to create any nodes that have less than 10 cases. And we say CP equals 0, meaning with this constraint, go and generate as big a tree as you want. Okay, there is no further constraint we are putting through CP. When we study cross-validation and pruning, we'll learn a little bit more about what CP is. Okay, so this is the function we are using to print the tree. So Once you have done this, the variable bh.tree contains the tree that has been generated, and we use the PRP function to generate a pretty print of the tree. Okay, now this function, there are lots and lots of arguments that you pass to this function. You can look at the documentation for the PRP function, $PRP in RStudio. Once rpart.plot is loaded, you can do $PRP, and then you will see all the different options that are there. I've just done a little bit of experimentation and chosen these particular arguments that make the printout look the way we've been used to in this course. Okay, so we're saying type equals to one, depending on the type of node we want. Extra contains some information that is displayed. Once again, the documentation will tell you NN is true, which means we want the number of cases which are in a node to be indicated. Fallen.leaves equals true. That makes all the leaf nodes come at the same level, which is convenient. Otherwise, you could have leaf nodes appearing at many different levels, and that could be confusing. Factlen is 4, varlen is 8, meaning even if the variable name is very long, just cut it down to 8 characters. Shadow.color equals gray. We've seen that beneath every node there's a small nice looking shadow, and we want the color of the shadow to be gray. Okay, so all of this results in the tree being printed. And when you do bh.tree, that gives you a textual output of the tree, both of which we will look at shortly. Okay, so this is a tree that gets generated, and the appearance of the tree is controlled by many of the arguments that we have chosen here. Right, so for example, fallen.leaves equals true. That's what put all the leaf nodes together. Otherwise, you could have a leaf node there, another leaf node here, a leaf node there, etc. Especially this will happen when a tree has many levels, and leaf nodes can occur pretty much at any level below the root. Okay, so it would be difficult to search and find them, but if they're all at the same level, then that gives a good indication of what to do, right? Shadow.color equals gray. That's what is creating these shadows. Okay, you can go and look at the documentation and actually try out some other arguments to get more information in the tree if you like. So the PRP function, calling the PRP function, generated the tree printout like this, the graphical representation of the tree. This command bh.tree, just basically the name of the variable that contains the tree, that will produce the textual output. Okay, the graphical output and the textual output contain pretty much the same information. And in this slide, I have put them both together so that we can look at them. So first of all, if you look at the graphical output, we already know that within every node, the majority case in the node is noted. So for example, in the root node, high are in the majority. It is these two nodes as well, whereas in these two nodes low are in a majority. Okay, and then it gives you the proportions of the different classes. In this case, the only two classes are high and low, so it's telling you that the proportions are 52 and 48, 52% and 48%. And of course, since the majority in this node is marked as high, so we know that the first number represents the proportion of high and the second number represents the proportion of low. Okay, and that is why this is classified as high, because high is in a majority. Okay, and then it tells you beneath every node, it tells you which variable, which attribute, and at what level was the split taken. So this tells us that this split occurred on the attribute named lstat, and values less than equal to 11 went to the left, and values less than 11 went to the left, and greater than equal to 11 went to the right. So that's fine. And it also tells us what proportion of the total number of cases coming in went into each node. So for example, all 100% obviously went to the root node. 51% went left. In other words, 51% satisfied the condition lstat less than 11, and 49% satisfied this condition of lstat, did not satisfy the condition of lstat less than 11. Okay, now this finally we can note that 45% of all the cases landed up here, 5% landed up here, 49% landed up here. You may be wondering, well, is it not supposed to add up to 100%? It is, but these numbers have been rounded off. Okay, just so that the node information is not crowded. Okay, so usually they will add up to 100 or 99. Okay, they avoid printing too many decimal places here at all. So just to make sure that this is not crowded. Okay, so notice also that the nodes are numbered. So if for any node, its child nodes have the numbers 2n and 2n plus 1. So for example, this is node number 1 as is shown on top, and its children will therefore be 2 and 3. For node 2, the children will be 4 and 5. That is 2 times 2 is the left node, and 2 times 2 plus 1 is the right node. Okay, so 4 and 5. If this had children, they would have been 6 and 7. It doesn't have any child nodes. Okay, that's the numbering. And of course, the numbering in the graphical output matches the numbering in the textual output. Okay, so the information here is the same as the information contained in the first row. Okay, so the first thing that you see here is what kind of split occurred, created that node. Okay, what kind of split created the node? Here it is basically saying, well, no split created this node, this is a root node. That's what you're seeing here. Following that is the number of cases that came into the node. Okay, so in this case, this 255 tells us that this 100% is really 255 nodes, right? So 255 nodes came in here. That's what it tells you. And the next number tells you, and of course this tells you that high was in a majority. This number in the middle tells you how many cases were in a minority. Okay, so 122 cases were in a minority. Okay, and out of the 255 cases, that's what they call as the loss. Okay, so that was the composition of this node. It had 122 of low and 133 of high. That's what this node had. Okay, so the node number 2, it says what condition was satisfied? LSTAT less than 11.375. Okay, here it's just printed as 11, but it's actually, again, to avoid crowding, they didn't print all the decimals. So the actual split occurred on LSTAT less than 11.375, and all those things came here. Okay, so 129 cases satisfied this condition. Okay, out of those 9, again the majority was high, so 9 of them were low, 120 of them were high. That is what this information is telling us. And here you see the actual proportions, right? So here it said 52:48 on the root node. Well, it's actually 0.5215, etc., etc. This is just rounded off to 2 decimal places. Okay, so now if you look at node 3, again you see that the split that created that condition, that node, was LSTAT greater than or equal to 11.375. Okay, so that's the information that is contained in the textual output. You can see clearly that pretty much the same information is contained in both of these. This shows the information with a little greater accuracy. Okay, and then it gives us a little more information on the composition of the nodes. Okay, which also you get here, right? You get the percentages, and then with the numbers you could work it out. Okay, now in the textual output, the leaf nodes are marked with a star, right? In the graphical output, it's pretty clear what the leaf nodes are. In the textual output, unless they specially indicate to us, we won't be able to find out. Well, we can. If we follow the node numbers, we'll be able to find out. But it's more explicitly pointed out by just putting asterisks. Now let's move on to take a look at how to generate the error matrix on the training partition, then make predictions on the test partition, and finally generate the error matrix on the test partition. Okay, so in order to generate predictions on any partitions, in fact this is quite common in R, when you want to make predictions, use the predict function, right? So the arguments to the predict function are what model to use to make the predictions, right? So predict is the name of the function, and we want to use the model bh.tree because that's what we call the model here. We call the model bh.tree. Okay, and then the data on which to perform the predictions. Again, we want to make predictions initially on the training partition, so we say train. And as I've already pointed out, you can have a model prediction either make an actual class prediction, meaning predict a class based on a default cutoff of 0.5, or you can just ask the prediction function to give you probabilities. Okay, we'll be looking at probabilities later. For now, Let's say we want the function to simply use the default cutoff of 0.5 and generate predictions. If you wanted to do that, you say type equals class. Okay, so rather than predicting probabilities, well, just give me the class. Tell me whether it's high or low by using the default cutoff. Okay, so once you have that, we can then generate the error matrix, right? Because we have the actual values contained in train $medvcat, and then we have the predicted values contained in this vector pred.train. Okay, so I can generate the error matrix by using this function table. Okay, table train $medv underscore cat, the actual values, pred.train, the predicted values, and we are saying that we want to put these names. The first thing is the actual values, the second thing are the predicted values. Now shortly we'll be looking at a slightly different way to do the same thing, right? Rather than write this third argument, we can just say actual equals training $medvcat, comma, predicted equals pred.train, and then we can leave this third part out. I'll show you both. Right now I'm showing you this option, but I'll predominantly switch to using the other option going forward. Both of them work the same way. Okay, so what this does is it generates this error matrix. Okay, so what we see is that of the 133 actual high cases, 114 are predicted to be high and 19 are predicted to be low. Of the cases, of the 122 cases that are actually low, only one is predicted as high. Okay, of course, let's assume that high is our positive case. Okay, that means you have 114 true positives and 19 false negatives, right? Because if high is the positive class, low is the negative class, these 19 are not really low. They are predicted to be negative, but they're not. So they're 19 false negatives. Okay, this one low is a false positive because it's actually not a high, but it's being predicted as a high. And this is true negatives. 121 are actually low and predicted to be low. Okay, so these are all the predictions that you're making on the training partition. Now, whether these are good or bad depends upon our context, meaning it all depends upon what can you do without the model, what can you do with the model. Nevertheless, even assuming that this is good, we can't just start using this model because we first have to test out the model on the test partition, which means that we have to start making predictions on the test partition. So we are using the same predict function. We are putting the results in a variable called pred.test, and we are using the same tree. Only thing, we are switching the data. Instead of train that we used earlier, we are now switching to test. And again, we are saying type equals class. And once again, we go ahead and generate the error matrix. This time I'm using the approach that I mentioned earlier, right? I'm just saying actual equals this, predicted equals this. Then you don't have to give the third argument of DNN equals. That's not needed. Okay, so this again shows us how the performance is on the test partition. Okay, once again, whether the model is good or bad depends upon the context. What can you do without the model? What can you do with the model? Is there any benefit? Okay, if this model performance is actually decent by our criteria, then we can start using this model. In other words, we can deploy the model.